Hello students, in today's class we are going to study the different types of molecular orbitals, and these molecular orbitals are bonding molecular orbitals, anti-bonding molecular orbitals and non-bonding molecular orbitals. According to the molecular orbital theory, there exist three primary types of orbitals over here, and these orbitals are formed by linear combination of atomic orbitals. These are given as, over here you can see there's anti-bonding over here. What exactly is anti-bonding? Always remember, in anti-bonding the stability is the least, and because the stability is the least, the energy is the most. The electron density is concentrated behind the nuclei of the two bonding atoms in anti-bonding molecular orbital. This results in the nuclei of the two atoms to be pulled away from each other. These kinds of orbitals weaken the bond between the two atoms. Let us take an example. I have a nucleus over here. I have another nucleus over here. And both these nucleus have an orbit of electrons besides it. Even over here, I have an orbit and I have an electron besides it. Now there is one electron over here and one electron over here. This is like the normal scenario. Now let me show the scenario of anti-bonding. What happens in anti-bonding? I'll just erase these electrons from here and I will place them in the opposite direction. One electron will be over here, one electron will be over here. But the electrons are behind the nucleus. After that also, if at all a weak bond is being made, this bond is not strong. If the bond is not strong, the molecule itself is unstable. And if the molecule itself is unstable, then the energy will be quite high. So this is the anti-bonding molecular orbital. Moving on, we have the non-bonding molecular orbitals. In the case of non-bonding molecular orbitals, due to complete lack of symmetry in the compatibility of the two bonding atomic orbitals, the molecular orbitals have no positive or negative interaction with each other. These types of orbitals do not affect the bond between the two atoms. Again, let me make an atom over here. It has a nucleus. This also has a nucleus. This has an orbit over here. This also has an orbit over here. If I have an electron over here, both of these electrons are not going to take any kind of participation. There is no participation. And if there is no participation in the entire bond forming process, there is no impact at all. Thus, there is no impact as well. So, these are the non-bonding molecular orbitals. So, if you see the formation of molecular orbitals, an atomic orbital is an electron wave. The waves of the two atomic orbitals may be in phase or out of phase. For example, you have over here A psi B represents the amplitude of the electron. So, if you see over here, if this is the amplitude of A, over here this much is the amplitude of A, this much is the amplitude of B. Over here this particular amplitude of phi is A plus B, psi A plus psi B. So when they are in phase, make sure to remember this. When they are in phase, there is addition of amplitude. And why not? Why won't the amplitudes add themselves? If I have a wave over here which goes like this in this particular direction, let's name this wave as wave A. If I have another wave over here which again goes in the same way, let's name this wave, this direction, let's name it as wave B. I have wave A, I have wave B. Now, if both of them are in the same phase and we are making another big wave out of it, I'm just drawing it over here. It will be a bigger version of wave. And this particular thing will be nothing but A plus B going over here in this direction. So this is how you get that. This is the first case wherein the two waves are in phase. The important word over here is in phase. The waves have to be in phase. If the waves are not in phase, then they will not add up. Case 2, when both the waves are out of phase, then we'll have to subtract. Again, let me make two waves over here. I have wave A going in a particular direction. I have wave B. Let's make wave B a little smaller, going in the opposite direction maybe. Now these are out of phase. Important word over here is out of phase. So if both of them are out of phase, the product that I'll get, let me make a product. Now this will be nothing but A minus B. Over there we had addition. Over here we'll have subtraction. If it is in phase, you need to add. If it is out of phase, you need to subtract. So over here, if you see this particular wave, for this the phi is nothing but psi A minus psi B. And it is not the addition of both of them. Let us see the characteristics of bonding molecular orbit. Now what are bonding? Bonding is nothing but the bond will be strong. Before we see the characteristics, let us just see the three different types of molecular orbits. We have bonding, we have anti-bonding, and the last one we have is the non-bonding. In bonding, they are generally in phase. In anti-bonding, they are out of phase. And this does not have an impact at all. In bonding, there is greater stability, lower energy. Over here, you have lower stability, greater energy. So these are like some of the basics of the bonding, anti-bonding, and non-bonding molecular orbit. Now we are seeing the features or the characteristics of the bonding molecular orbit. The probability of finding the electron in the internuclear region of the bonding molecular orbital is greater than that of the combining atoms. Let us draw a bonding one. Over here, whenever we are talking about bonding, we have to make sure that the bonding has two electrons which are in the middle. That means a nucleus here, one orbit. Now we generally draw one orbit and one electron because I want to give you the simplest forms of example, simplest versions of example. We can complicate it if we want later, but as of now we need to understand the concept. Electron here, a bond is being formed. So over here the region of the bonding is greater than of the atomic orbital. Over here this particular orbital will be now considered as a molecular orbital. So the electrons are no more of atomic orbitals, but they are now of molecular orbitals. And thus we find a good way to make a particular molecule. H atom and H atom come together to form H2 molecule. Why? Because the electrons are in the molecular orbital instead of being in the atomic orbital. The electrons present in the bonding molecule orbital result in the attraction between the two atoms. This is very important. Attraction. Why are we talking about attraction over here? Because whenever we want to make two different kinds of atoms meet together and make a molecule, over here at this point of time there should be attraction for a bond to be. The bonding molecular orbital has lower energy as a result of the attraction and hence greater stability. As I've written over here, greater stability, lower energy. As simple as that, very simple bonding molecular orbitals. Now we have in phase, this was also written over there. They are formed by the additive effect of the atomic orbitals. That means they are in phase. The main word which we need to write over here is in phase. And because they are in phase, we will add them. Addition is important. They're represented by sigma, pi, or delta. These are simple representations. Now let us see the characteristics of anti-bonding molecular orbits. Anti-bonding molecular orbits are opposite of molecular bonding orbitals. Now why are they opposite? Because if I say in bonding the stability was high and energy was low, this will be opposite. The stability will be low, the energy will be high. In bonding, if I say that they were in phase, over here they are out of phase. In bonding, there was a attractive force, there was attraction happening to make the bond. Over here, repulsion will happen. In bonding, the bond was strong. Over here, the bond will be comparatively weak. And all these points are very important when it comes to the anti-bonding molecular orbits. Let me first start off by drawing two atoms just to explain. Again, drawing minimum number of orbits, just one nucleus, not even showing the protons and the neutrons, only keeping the stuff which is necessary in this particular example. Drawing the orbits. I have one electron over here, one electron over here. There's a lot of distance between both of them, and thus there will be repulsive forces. The probability of finding an electron in the internuclear region decreases in the anti-bonding molecular orbits. Now what do we mean by internuclear region? So when this particular thing will form a molecule, it will form something like this. Nucleus taking this particular orbit, again nucleus taking another orbit. In this particular region, this region over here, which is there in the middle, this region is known as internuclear region. This is the region where we should have found out our particular electrons, but we will not be able to find them. Why? Because we are talking about anti-bonding, and that is the reason why they will be over here somewhere. The electrons present in the anti-bonding molecule orbital result in the repulsion force. As you can see, there is no attraction, there will be repulsion. The anti-bonding molecular orbitals have higher energy because of the repulsive force and lower stability. They form a subtractive effect. Over here, the important thing is subtractive. Now, what do we mean by subtractive? They are out of phase. We had seen in phase and out of phase. In phase, you need to add both of them. Since these are out of phase, you'll have to subtract both of them. They are found by subtractive effect. That is, it's psi A minus psi B. Now, if you remember the symbols of the bonding molecular orbital, they were sigma, pi, and delta. Over here, since these are opposite, there are sigma asterisk, or you can call it as sigma star, pi star, and delta star. Completely opposite of bonding molecular theory. Why are anti-bonding orbitals high in energy? Always remember, whenever we are talking about energy, we're talking about two things: stability and energy. Since the stability is to the rock bottom, the energy will be high. Always remember, something which is stable will not have high energy. If you are stable, now what is a human being positioned to be stable? If we human beings are sleeping, we are considered to be stable. If we are sleeping, do we have a lot of energy? No. But do we have a lot of stability? Yes. So energy and stability are inversely proportional to each other. What if we are jumping? If we are jumping, a human being jumps with energy. So when we are jumping, do we have a lot of energy? Yes. But do we have a lot of stability? I doubt. No. So over here also in anti-bonding, the energy levels of bonding molecular orbitals are always lower than those of the anti-bonding molecules. This is because electrons in the orbital are attracted by the nuclei in case of bonding molecular orbitals, whereas the nuclei repel each other. I'll just draw it again so that you all can understand where the repulsion exactly is happening. Nucleus orbit, the second orbit, electron, electron. We wanted a connection between this and this electron, but instead I can see two nuclei coming together, giving us repulsion. Why? Because this nuclei has a strong positive force. This nuclei is also a strong positive force. Positive and positive repel. Negative and negative repel. Positive and negative attract. Negative and positive attract. Since over here I have positive and positive, it will give us a repulsion force. Now let us see the difference between the bonding and the anti-bonding molecular orbitals. The first one is the bonding molecular orbital. We'll see them point by point, but we'll see both the points together. So the first one is molecular orbital formed by the additive force. Over here we have psi A plus psi B of the atomic orbitals. It is called as bonding molecular orbitals. For anti-bonding molecular orbitals formed by the subtractive force, that is psi A minus psi B, are nothing but my anti-bonding molecular orbitals. The second point is probability of finding the electron is more in case of bonding orbitals. That is but obvious because they are giving us the bond, and then we can find the electron in the bond. The probability of finding electrons is less in the anti-bonding molecular orbitals. There is also a node between the anti-bonding molecular orbitals between the two nuclei where the electron density is 0 because there are no electrons. The nuclei are repelling each other, thus there are no electrons present over there. Over here if you can see, they are formed by combination of positive and positive with the part of electron wave, and over here they are formed by an overlap of positive and negative. The next point is very important because it talks about electron density. Electron density in the bonding molecular orbital in the internuclear region is high. That means the region between the two atoms is high. So if I'm talking about bonding, let me just write bonding over here. I've told you what is internuclear region. If I have two nucleus, this is an orbit. Let me just make this nucleus a little more nearer so that I can show the internuclear region very clearly. Just making this nearer, making another orbit. So the electrons will be here. The probability of finding electrons in this particular region, the internuclear region, is high. Now if I'm talking about anti-bonding, some people also call it as anti-bonding. Both of them are same. The logic is same. What happens in anti-bonding? Nucleus, nucleus. Two nucleuses are there. I have two overlapping orbitals as well. But electrons are nowhere to be seen inside this particular internuclear region. The electron density in the anti-bonding or anti-bonding molecular orbital in the internuclear region is very low, and so the nuclei are directly exposed to each other. If you see over here, the nuclei are directly exposed to each other. Therefore, the nuclei are less shielded from each other. This particular thing leads to repulsion because both the nuclei are positive, nuclei are powerful, they have protons, they have neutrons, so they are positive as well as powerful. Thus, this leads to repulsion. The bonding molecular orbitals. Over here in the bonding, I have sigma, pi, and delta. But in the anti-bonding, I have sigma star, pi star, and delta star. Both of them are opposite of each other. The lowering of the energy of bonding molecular orbital than the combining atomic orbital is known as stabilization of energy. And similarly, increase in the energy of anti-bonding molecular orbital is known as destabilization of energy. Always remember, if I'm talking about bonding over here, if I am writing, let me write it over here. If I'm talking about bonding, over here the atomic energy, that means in the atomic orbitals, the atomic orbital energy will be greater than the molecular orbital. Oh, I made a mistake. Molecular orbital energy. And this process, this entire process which is there over here, is known as stabilization. It stabilizes the energy. But if I'm talking about anti-bonding, let me just write it over here. Anti-bonding. In anti-bonding, what happens is the atomic orbital energy will be much lesser. And thus over here, I will put a lesser than sign over the molecular orbital energy. And this process, this because it is lesser, this particular thing is known as, let me write it over here, destabilization of energy. Over here, energy decreases. Over here, energy increases. Features of the molecular orbital theory will be like another topic. We'll make another topic on features of molecular orbital theory. So this ends over here. So with this, we studied the bonding and the anti-bonding of orbitals. We also studied the non-bonding orbitals, but the non-bonding orbitals did not have a much greater kind of impact over the chemical bond or over the atomic or molecular orbitals. So the main things that we studied were what are bonding, anti-bonding, and non-bonding molecular orbitals. And then we studied the difference between the bonding and the anti-bonding ones. I hope you understood the entire video. Thank you so much for watching this video. Thank you.